Hello everyone, I'm Hyungmin Kim from Triple ICLR Lab. Today I'll present the SimuHome, a benchmark paper accepted as an oral at EURIPS 2025. The work addresses a well-defined gap in the evaluation of LLM-based smart home agents. Existing benchmarks treat the home as a static system and consequently provide very little signal about an agent's ability to reason about temporal and environmental dynamics. This is the index of my presentation. A useful frame for what this paper is about is the example shown here. The user issues an indirect contextual utterance, a complaint about discomfort with no explicit imperative. A competent smart home agent must perform several reasoning steps in sequence, recognize that an action is being requested, infer the latent goal, query the relevant device or environment state, and only then issue an appropriate command. The reasoning trace on the right exhibits exactly this pattern. The agent identify low illuminance as the underlying cause, formulate a plan to retrieve the current illuminance level, and selects the appropriate API call. This is the behavior we would like agents to exhibit. The empirical question of this paper poses is the extent to which current LLMs do so reliably across query types of increasing complexity. As the failure analysis will make clear, the answer depends critically on whether the task involves temporal or environmental reasoning. The methodological landscape can be partitioned along two axes: environment fidelity and temporal grounding. The first generation of LLM smart home benchmarks operate on static state snapshots. They evaluate command understanding and API selection, but treat the environment as a frozen object. Actions do not produce downstream consequences, and time does not advance. A more recent line addresses anomaly perception over state sequences by SmartBench, but the underlying environment is synthetically generated rather than simulated. There is no executable model of how device actions affect environmental variables. SimuHome occupies the third position, an executable simulator with continuous temporal dynamics over heat, humidity, and illumination. Because device action induces future state changes, the agent must reason about consequences, not just commands. The methodological claim follows: evaluating on static benchmarks systemically overstates agent capability because it removes the very dimensions along which contemporary models are weakest. Once the environment evolves over time, the gap becomes visible. The paper makes three contributions. First, a time-accelerated meta-native simulator. Environmental variables evolve under physics-inspired models, thermodynamics for temperature, decay toward ambient for humidity, and so on. Because the API surface conforms to the Matter protocol, an agent that succeeds in simulation can in principle drive real Matter-compliant hardware. Second, a benchmark of 600 manually validated episodes spanning 12 query types in a 4-level taxonomy. Crucially, each query type is constructed in both feasible and infeasible variants, paired against matched initial states. Third, a reproducible evaluation framework, hybrid grading that combines deterministic simulator checks with LLM as judge scoring, an explicit error taxonomy, and a post hoc failure recovery protocol. The result is an evaluation pipeline that supports fine-grained diagnosis rather than a single aggregate metric. The architecture diagram shown here is reproduced from the paper. The leftmost component is the home environment, a configurable layout of rooms, devices, and a user model that issues natural language commands. The user query in this example is a request to start the washer. The next component is the metadata model, which defines how every device is addressable. Each physical device has an endpoint. Each endpoint exposes one or more clusters. Each cluster contains attributes, the device state, and commands, the actions that may be invoked. This is the abstraction layer that real matter-compliant devices use. The agent operates against this abstraction. It receives the natural language query and produces two calls. In the example, it issues an on-off on command on the washer's endpoint, followed by an operational state start command. Communication is mediated by API requests and responses. The rightmost component is the server, the SimuHome simulator, which holds the device state and applies environmental updates over time. The state transitions visible in the figure show the operational state moving from idle to start and the on-off attribute flipping from false to true. The architectural commitment to make is the agent server boundary. The agent only ever speaks matter. This is what supports the deployment readiness claim. Substituting real hardware for the simulator does not require changes to the agent. The 12 query types fall into 4 families ordered by reasoning difficulty. Qt1 is state inquiry. The agent reports the current value of a device or environment variable. This is essentially a retrieval task. Qt2 is implicit intent. The agent infers the latent goal from indirect or contextual language. The example shown, it feels sticky in here, admits multiple plausible interpretations. The correct inference here targets humidity rather than temperature. Qt3 is device control. Explicit, possibly multi-step actuation, respecting device preconditions and operational states. Qt4 is workflow scheduling. Schedule one or more actions against a future time or future environmental state. This is the level at which the most pronounced capability gap will appear. The design choice step becomes important during evaluation. Each query type is paired with both feasible and infeasible variants. Critically, infeasibility is determined by the simulator state, not by surface features of the prompt. An agent must therefore actually inspect state to judge feasibility. It cannot detect contradictions from text alone. Especially, Qt4 is the core of the benchmark. It decomposes into 3 subtypes, distinguished by the form of temporal or environmental dependency the agent must reason over. First is absolute time. The agent must convert a natural language time reference to a simulator timestamp and register a workflow. Second is relative time. The agent must additionally perform arithmetic on the current clock to derive the target timestamp. Third is environment conditioned. The agent must reason backward from a target environmental state to determine the action time, taking the environment's dynamics into account. The three subtypes impose increasing demands on reasoning over time and over future states. The benchmark is constructed into three stages, illustrated by the figures at the bottom. Stage 1 is state construction. For each scenario, the simulator is initialized with a plausible household configuration and advanced through a sequence of sampled actions. The figure shows a wash and air purifier scenario unfolding over 30 minutes of simulated time, producing a coherent initial home state. Stage 2 is goal and prerequisites action generation. From that state, the system samples target devices and target attribute values and identifies the prerequisite tool calls, for example, the room discovery calls, that an agent must make to ground its plan. Stage 3 is query synthesis. A natural user utterance is generated, conditioned on the scenario, the query type, and the feasibility label. The example shown demonstrates the linguistic variety the procedure aims for, an indirect conversational request rather than a templated command. Each episode is then manually validated. The benchmark contains 600 episodes total, with feasible and infeasible instances balanced across query type. The evaluation methodology can be stated as a single principle. Feasible tasks are graded by the simulator. Infeasible tasks are graded by LLM judges. The reason for the split is the nature of the correctness criterion in each case. For feasible tasks, correctness is a property of the simulator's terminal state. Did the scheduled action fire at the right time? Did the target device end in the correct state? Were the required prerequisite calls made? Because the simulator is deterministic, this can be checked by direct assertion. On the other hand, for invisible tasks, correctness is not a state property but a semantic one. Did the agent recognize the contradiction, and did it respond appropriately by refusing or flagging the false premise? Such judgments cannot be reduced to state assertions, so they are evaluated by three LLM judges. The methodological commitment is that the grading mode is dictated by the correctness criterion, not chosen for convenience. Mixing models inappropriately would produce non-reproducible scores. The per category mapping is itself a non-trivial design contribution. The full results table is reproduced here. Models are grouped into four bands by scale and reasoning capability. Small open source models, larger open source models, closed source non-reasoning models, and reasoning models. Three patterns are worth noting. First, performance is broadly monotonic in the Qt difficulty axis. Scores are highest on Qt1 and it collapses on Qt4 for nearly every model. Second, The model scale axis interacts strongly with this difficulty axis. Small open source models exhibit a near zero floor across Qt4 columns. Frontier non-reasoning models recover substantial performance on Qt1 to Qt3, but remain markedly weaker on Qt4. Only the reasoning models close most of the gap on Qt4, and even they exhibit a residual deficit on the hardest subtype. Third, the gap between feasible and infeasible variants is informative on its own. Many models that perform reasonably on feasible cases degrade further on infeasible ones, indicating that detecting infeasibility is a distinct and harder competency than executing feasible plans. This slide isolates the per-Qt trend across three representative models. The shape of the curves is the point. Across Qt1 to Qt3, all three models exhibit a familiar scaling pattern. Larger and reasoning-equipped models outperform smaller models, and the gap is roughly constant. Crossing into Qt4, the smaller model collapses to a near zero floor. The frontier non-reasoning models retain some capability, but loses substantial ground relative to its Qt3 performance. The reasoning model retains the highest scores but exhibits its largest degradation. The thing is that Qt4 demands numerical forward simulation of continuous dynamics, which LLMs cannot perform internally. Scaling and reasoning techniques improve task decomposition, breaking the problem into substeps and arithmetic, but they do not improve simulation accuracy. The authors classify every failure manually. 5 categories cover the feasible failure surface. First is environment perception. It is the failures in interpreting sensor output, including out-of-range readings parsed as ordinary values. Second is intent inference. This is the misinterpretations of ambiguous user intent. Device control means selecting the wrong device or violating a precondition. Action planning is incomplete execution of multi-goal queries or violations of logical action ordering. Last, temporal reasoning is the errors in time arithmetic or sequence alignment. The taxonomy extends with three categories that apply only to infeasible episodes: contradiction mishandling, contradiction blindness, and LLM judge. First, contradiction mishandling is the failure in which the agent detects the infeasibility but does not refuse appropriately. The trace made the pattern explicit. The agent's own reasoning literally states that the task is impossible, yet instead of refusing, it improvises an action on a different device. The diagnostic point is that this is not a knowledge or perception failure. The relevant information is present and surfaces in the agent's own output. The failure occurs at the response policy stage. The agent does not commit to refusal, and when the simulation requires it. Contradiction blindness is the structurally distinct failure. The agent never detects the contradiction. The same scenario as the previous slide, but now the agent commits a workflow that the simulator's own thermal dynamics will refute, with no recognition of impossibility anywhere in its reasoning. This is the dominant failure on Qt4 invisible across the entire model panel. It persists across model scales, including reasoning models, with a residual rate that scaling does not eliminate. The implication is that the model cannot internally simulate the environment with the precision the task requires. The natural remedy is an external validator that evaluates plans against environment dynamics before commit. So this is the result. In feasible cases, device control dominates at Qt2 and the distribution flattens at Qt4. Feasible workflow failures arise from many sources with no single dominant mode. In invisible cases, Qt2 invisible is dominated by mishandling. Qt4 invisible is dominated by blindness. The contrast is structurally meaningful. The failure mechanism shifts with the reasoning demand. Implicit intent contradictions surface in the agent's output. Detection succeeds. Response, response policy fails. Temporal environmental contradictions do not surface at all. Detection itself fails. The recovery experiment asks whether models can correct themselves given execution feedback. A failed episode is replayed with structured error information wrapped in a conversational user simulation turn. The agent revises and retries. The trend is the relevant binding. Recovery rates rise monotonically with model capability, and stronger models recover a substantial fraction of their own prior failures. So, the capability is present, the verification is absent. Models that cannot detect their own contradictions before execution can frequently correct them once contradictions are pointed out. The bottleneck is not reasoning competence, but the absence of a self-verification step in the agent loop. The diagnosis converges on a single architectural prescriptions, move verification from after the fact to before commit. The current paradigm, act then hope, places the entire verification burden on the agent itself, which the failure analysis shows to be unreliable. The proposed paradigm, verify then act, inserts an explicit verification stage between plan and act, populated by tool-based queries of the current state and pre-execution simulation of the plan against environment dynamics. However, they have four limitations. The benchmark is single user. Multi-user arbitration is out of scope. And the simulator is fully deterministic. Agents may overtrust environment predictions in less regular real-world conditions. The schedule workflow API does not pre-validate schedules commands by design, mirroring production's smart home systems but placing the verification burden on the agent. And the judge model identity is specified in configuration but not stated explicitly in the paper, which has been observed to produce reproduction drift. To summarize, under continuous temporal dynamics, current LLM agents exhibit a structural failure mode on workflow scheduling that scaling does not eliminate. The paper's prescription is architectural, an external verification stage before action commit. Thank you for listening.